next we have Brandon Yates from Development to Faucet. Brandon, take it off. Thank you, sir.
Yep. All right, thank you. Good morning. Welcome to DevOps Days. My name is Brandon Yates, and I'm going to talk about how we go from a development faucet to a development pipeline. And like I said, my name is Brandon Yates. I'm a senior platform engineer for the mobile team at Fleetio. And platform engineers at Fleetio, we're a mix of DevOps, site reliability, developer productivity, the whole 9 yards. I have experience in companies of all sizes, from the smallest startups all the way up to General Dynamics, which has about 30,000 employees worldwide. So I have seen every type of development pipeline imaginable, and I just want to talk about how they work. So here's the overview. We're going to talk about how we scale development processes from a faucet to a pipeline. What is a development pipeline? What makes an effective pipeline? What common problems do our pipelines face? That's what all of us here do, right? We work as part of these pipelines, and we think about them. We wake up in a cold sweat at night as the solution to our issues comes to us. So how do we optimize these pipelines, and how do we scale them as our organization grows? These are the questions that drive our business. So a development pipeline, it's a series of processes which translates requirements into a software end product. It's the value driver of our engines, that's 65% of the global economy. It's similar to a factory assembly line. You have inputs and you have outputs. And it's generally accomplished through CI/CD. And it's maintained by us DevOps engineers. So we've got the common tool sets, your requirements, Jira, your version control, GitHub, your IDEs, your other developer productivity tools, your Circle CI, CI/CD in the cloud pipelines, your deployment environment, Docker, Kubernetes, AWS, the app stores, whatever. And we have these general stages from the requirements, the building, the testing, the deploying, the validating, the measuring, and then we do it all over again. And there's many ways to feed this process back into itself, but it all sort of boils down to the same circular flow. All right, so what are the characteristics of a pipeline? What are the chief concerns when we think about how do we measure this thing? How does it function? So the principal characteristic is the throughput, right? This is the value add, and this is how quickly that we add it. So in Agile, this is often referred to as the velocity. An example would be, in the last 2 weeks, our team pushed 10 commits to production. And what that really boils down to is the profit equation. That's how much value we deliver to our customers. That's how we competed. You know, some other company, maybe they did 13. Or their commits were a higher quality. And so that's really the principal thing that we're all here for, right, is the throughput. Next up is the capacity, which is how much work occurs simultaneously, and then sometimes that's called the bandwidth. This one is really easy to mistake for throughput. A lot of times we feel like we're having a high level of throughput, and really, we're just working on lots of things at the same time without producing more in a shorter period of time. And that brings us into latency, which has how quickly it takes a single piece of work to go through your workflow. And that's super important because sometimes you need to push something through. You have a critical bug fix, you have a big deal that comes in, they say, hey, if you don't have this thing, we walk, and you just need to push it through as fast as possible. And with a big organization with all these different tools and processes, it's really easy for that time to creep up such that you can't make quick maneuvers like that. So your throughput is a combination of your capacity and your latency. And we'll talk about more of that in the next slide. The next thing is your quality. It doesn't matter if you're producing a lot of material, if it's bad. So it's a measure of how well your end products meet the requirements. The next thing is the reliability, which is how does your pipeline perform over time? It could be reliably good, it could be reliably bad, or it could be inconsistent. And that will have a big driver of your reputation and of your bottom line. And then finally, at the end of all this, in some ways the least important thing is the cost, is how much does the pipeline cost to build and how long does it cost to maintain, both in time and in dollars. All right, so here we have a nice visualization of the relationship between throughput, capacity, and latency. And essentially your throughput is how many capacities can I push through the latency time period at a time, right? So let's say you have 5 issues that you could work simultaneously. How many of those 5 issue increments do we get through in our time period? Most of the time we look at 2 weeks. Some companies do every week. At Fleetio, the mobile team produces once a week, and that's our latency period. So in the previous slide, we saw this nice, smooth, consistent pipeline, but in reality, they don't look like that. They have bottlenecks, they have different characteristics at different stages, so certain stages might have high capacity, low latency, or the other way around. And the name of the game is to optimize all these different parts of your pipeline together such that they produce a smooth experience, right? It's not good to have things speed up and slow down and have good quality here and bad quality at the next. We have to look at this entire thing together, this big complex system, and make sure it hums along. So what would be an ideal development pipeline? If you're a business owner, if you're a software team, and you were given a genie, and he said, well, what is your wish for your development pipeline? What would we wish for? Well, we want a high throughput. We want to produce a lot of features very quickly. And to do that, we need a high capacity, and we need a low latency, and we need those features to be of high quality, or no one will buy them. They won't help anyone. And then we want it to do that consistently over time for many years. And we don't want to pay through the nose for it, right? So how do we achieve that? Well, like most things in engineering, you achieve your goals through effective trade-offs. So if you're a project manager, you'll be familiar with the familiar trade-off of quality, speed, and cost, which you can usually have 2. You can have high quality and quick to market, but it's really expensive. Or it could be inexpensive, but the quality might not be so good. Well, with the development pipeline, we unfortunately don't have this simple rock, paper, scissors equation. We have rock, paper, scissors, lizard, Spock, where we have these 5 different diametrically opposed characteristics, and we get to choose 3 of them generally. Now, there are some virtuous cycles you can get into where you can improve all of these at the same time. But in general, depending on the stage of business that you're at, you're going to have to choose what's most important at that time. All right, so when I talk about a development faucet, what do I mean? Well, at the early maturity companies, you have a faucet, right? Like you don't have very much coming out of the end of this thing. It's inexpensive, it's quick, it's an early process. You turn it on, and the water comes out immediately, but not very much water comes out, right? So it's hard to have a thriving business empire to deliver water to a family or a town or a city with just a faucet, right? So we need to scale this thing. We need a pipeline. We need more water all the time. And what are the characteristics of that? Well, they take a long time. There's no real way to just go from nothing to this overnight. And it takes a lot of money, it takes a lot of skilled people working very hard. And it has high throughput, driven off the back of its high capacity. But then it usually has a high latency. They're slow. It's very difficult to scale and still have a quick run through of things just because there's so much more complexity in the system, so much more need for validation. All right, so we're going to return to this idea of bottlenecks. And what are the common bottlenecks? Well, the number one bottleneck that I see in software teams today is the validation bottleneck, We produce a lot of features, and we get them out really quickly. This idea of move fast and break things has really caught on. But effectively validating the performance and quality of your software is really underinvested in. A lot of times, we don't even know if our software is performing. There's just no visibility, and that really drags you down. The next one is the build and deployment process, that feedback loop of the compiling. There's that old meme of the developers sword fighting in their chairs as they wait for their code to compile. That's a huge drain, right? And then finally, there's the development bottleneck, which of all these three, this is probably the most focused on. Development is difficult. It takes lots of people thinking very hard and coordinating together. There's no magic solution. ChatGPT just isn't quite there yet and probably won't be for some time. So it's good for us to focus on the development stage because it's the heavy hitter. But it's also easy to over-focus on the development stage when you need all of them to work together in concert. All right, so let's consider the most basic pipeline possible. This is the Faucet, right? We've got a single developer. They design, build, test, and deploy their software all locally. They just run it off their laptop, and people can go directly into there and access it from the web, right? So what do we need for this? Well, it's very simple. All you need is a computer, maybe some development software, a person, and coffee. Which, that's obviously a joke, though, stimulants do help. Okay, so what happens then when we add our first developer, right? So we went from this fully serial process. It's very simple, it's very cheap, it's very efficient, but it's just not capacity enough. We just don't get enough throughput. We have more work, so we add another person. What happens then? Well, we don't get double the output just because we doubled our inputs, right? This is an example of Amdahl's law, which was authored really to discuss hardware machinery, but it really applies to any parallelable process, which that's what software development is, right? There's also a kind of an idea that there's some difference between the physical world and the digital world, that software somehow functions on different laws from the real world. But really, it's subject to all the same limitations. The same entropy that drags down physical goods, the same degradation, the same maintenance costs. It all goes into software. It's just a little bit harder to see. So when we talk about Amdahl's law, we're concerned with two values, right? The number of processors, which in many cases we can just consider to be the number of developers or the number of employees. And then have the F value, which is a fraction of a program that is parallelizable. And this is probably the single most important value to your business that nobody measures. If any of you have an idea of what this value is, like what percentage of your software tickets can be done in parallel, I would love to hear it. Does anybody raise their hand? I know what this value is with any degree of confidence. Yeah, see, I don't either, is the sad thing, is I know that this is a problem. I still don't have a good way to verify it. But I'm going to come up with one. So when we add a developer, it improves this right side of the equation, but it also introduces costs, right? And you see here it's in the denominator. That means that as that n number grows, the overall piece of that gets smaller and smaller. So really the upper limit is this F value. It's how good are we at splitting up our work? How efficient is the usage of the processors that we have? And that's really what we need to focus on to get really good results. All right, so here's a typical development team. You have more or less a serial design process. One person, more or less, creates the designs and the requirements. Then the expensive part, the development, we split that into 4 or 5, however. And then we validate again in serial. And that works pretty well for the most part. Otherwise, at this stage, you don't typically have the revenue to do fully automated QA, and a lot of these other things that would be super nice in theory, but at the scale are just impractical, right? All right, so now what do we need? Well, before when you just had a single developer, everything's just in their head. They don't have to really track anything, they know. But when you have multiple people, we're not mind readers. We haven't developed the use social characteristic. We don't have the hive mind yet. Thanks, Elon Musk, get my chip in my brain, right? But until then, we have to rely on issue management software. We need our Jira. We need a shared build environment. That's where our CI pipelines come in. And then we need an area to test before we put it into production. That's where staging environments, et cetera, come in. Those are all obvious. But here are the things that get neglected at this stage. And this is where it's really important to build good habits early. Linting and static analysis. When you have one person, they understand their own code. They have their own style. It's really easy when you start adding people to an organization to have different pieces feel different. And that introduces a tax that limits your F value. The amount that you can parallelize goes down when you have siloed areas of expertise. Ideally, all your developers can work on all parts of your code base equally as well. And one of the ways you can do this is with linting and static code analysis. The next thing would be automated building and deployment. It's really easy to just say, hey, you're the release captain, run these 5 commands. We don't really want to spend the time to add build scripts here. That's kind of overkill, but really it starts to eat up time as that 2-3 hours a week multiplied by every single week, multiple developers, that's a drag on that F value. And finally, you have your testing, your unit tests, your end-to-end tests, UI tests. Maybe you can't hit 100% validation here, but as we're going to see here in a second, your validation cost outstrips the features that you have. It is a multiplicative effect. As your system gains size and complexity, it becomes ever more increasingly expensive to validate. And if you don't get ahead of that validation curve, it will really limit your latency. All right, so we're going to demonstrate that validation cost scaling here. So in the beginning, we had feature A, and it was really easy. We validated it one time. It cost us 1 unit of validation. That's wonderful. But we need another feature. And A and B, they interact, right? We have a home page, and then now we have another page. So we get to validate feature A again, just to make sure we didn't mess it up. Now we got to validate feature B too, right? Okay, makes sense. We have 2 features, 2 validations. But here's the kicker. Now we have to validate the interaction between A and B. So it's not twice as expensive, it's 3 times. So as we keep adding features and we keep adding interactions, that cost scales multiplicatively between each feature and each interaction. And that's represented by this equation down here. So that means that by the time we have 5 features, just 5 features, that's not very many, it's single digits, one hand, and a few basic interactions between them, it now costs 15 times as much to validate your feature set as in the beginning when you had just 1. And so if you're not figuring out a way to scale your validation to this complexity, you're going to spend ever more time in that validation phase, or your quality will suffer dramatically. So here's what a typical dev department looks like. Now we've got more designers, way more developers. We've hired an additional QA person, and now we have a DevOps engineer, which is all great. This is all good things. This is an improvement over what it used to be. We used to not even have this person. The DevOps engineer didn't exist. It wasn't a distinct role. But we've learned a few things as an industry, and that's great. But this is still deeply unoptimized because it's not ahead of the validation curve. We are over-focused on the development stage. So we have this validation bottleneck where we have 2 people trying to manually validate the work of 10, 16. Think about your organizations and your validation process. I bet many of you have experienced similar problems. So this is where automated QA comes in. Now, Full-time automated QA developers are expensive. They can be hard to find. This doesn't necessarily represent a person. This is more an abstraction of time, the sort of the mythical man month. You can have your regular developers rotate into this role. But there comes a point very quickly when working on more features doesn't work you on more features. You just spin your wheels as you do ever-increasing capacity and an ever-increasing latency. And that's really going to only be paid down by investments in the validation and the support phase, that developer productivity that we just heard about. So what do we need for our large teams? How do we support a large team? Well, at this stage, you need to think about a release train management system. You need to think about your feature management. Can we do A/B testing? Can we turn things off and on in the wild? Do we have that analysis tool? Like I said, do we have a testing environment? At this stage, you're generally starting to attract more eyes. You need cybersecurity now. And as you add more people, you have a greater percentage of your time spent spinning up developer environments. It's time to automate the process of setting up your IDE. All right, here's the final thing here, and this is one of the main kickers. Tech debt. It's the invisible profit killer. So this is just a regular physical pipeline. It has rust and minerals accumulated, and it drags down the capacity. It drags down the latency. But you can't see it because it's inside the pipeline. And the same thing happens with our development pipelines. You have this accumulation of CRUD, your dependencies that are out of date, your code that was maybe not so good, that wasn't intended to live forever, but has now outlived its life cycle. All of those things accumulate, and if we don't see them, if we don't measure them, they go unaddressed. And the thing about tech debt is that it is debt. It does cost money. It does accrue interest. It's the same as any other sort of debt. It sits on your company's balance sheet as a liability, but your CFO doesn't know about it unless you tell him. And you may not know the exact dollar amount either. So that's one major area. Probably the number one cost to software right now is tech debt, because it sits out there unknown. It's the same metaphor as our physical infrastructure, which is coming due. So what are our key takeaways here? Well, the first is that we need a holistic approach. We have to consider the whole life cycle, the entire pipeline together. You can't optimize in a vacuum. The next thing is that we need to optimize for throughput, and we can't mistake capacity for throughput. And the last thing is that we need to invest in infrastructure. Everyone desires more features. You'll have your customers coming to you and say, I need a feature. I need a feature. And so you think, how do I get this feature out? And it is so easy from an organizational perspective to have the pressure at the beginning of the pipeline, that back pressure, draw all your focus to the start. So you're looking at the design stage, you're looking at the development stage, and that robs your sight and your attention from the later stages, which will really actually produce more features in the long run. So yeah, that's the gist of it. Check out these links for other things I'm up to, Fleetio, my private consulting practice. Thank you very much.
Thank you. Thank you so much, Brandon.